Good morning. Off to a little bit of a late start. Finally, someone else showed up in class. So we do have a lot to do today, and I'm going to get it done. That's my reason for getting the exam out earlier, and we'll get into that later. You can see a little bit of that on the screen right now because it's near the bottom. I have delayed grading papers. I went in that direction, but then I decided I wanted to just focus on this. I hope to get going on that, and you'll get stuff back from me as I get it done. And of course, the solutions will go out for problem set number 6 as soon as that is turned in. And the sooner that can be turned in, the sooner I can post the solution. So that'll all work towards working the exam, too. I hope the projector does something like not quit today, because if I look in the ceiling, I can see that they wired a different outlet in the ceiling from the other one close to the projector. That was per my suggestion, so everything that they've done kind of has been troubleshooting ideas I came up with. But it's like Dr. Trimboli told me a few minutes ago before he went off to class, it's another data point. We'll see what happens. We're trying to debug something for this classroom. So I'm going to switch off from the website. I'll just point out before we jump back over to this later, the exam 2 is a PDF that's linked here. It's also in the exam sections down below in the tabs if I eventually rearrange things between now and next week. So you can find it, same links down in here. And then there's a notebook sample, and I am going to use the notebook sample today in class to give you an idea of how it's useful and what you can do with it. So that's all premeditated by me to be able to take advantage of that. So there's a number of things in Chapter 5 that I want to get through. There's a lot of details that I don't absolutely have to go through, so I'm going to try to stick to the core of what I think is important. So from last week, we had, if I just dial back a little bit, we were overviewing in this chapter how we bring together the time domain, the frequency domain, and the Z domain, and start working with systems in a more holistic way. All three of those domains we work with new definitions, new topics at the systems level. So the focus of this chapter is systems, not signals, but systems and how we can look at them. So one of the things we looked at just as we were leaving last week is frequency response for rational system functions. This is just looking at it as a ratio of polynomials in the taken from the Z domain and writing it out in terms of poles and zeros. So the significance here is that working in terms of poles and zeros. And then the analysis here went in and looked at magnitude, phase, and group delay associated with the system. And we did those definitions last week, magnitude, phase, and group delay. And we'll be using them throughout today. So this is just generic results of modeling, phase unwrapping. But the focus right here is on geometric evaluation, how you can look at a pole and zero configuration and get an idea about what's going on in terms of the magnitude response, phase response, and group delay. So this is breaking it down, and it's this blue boxed equation here that allows us to do this geometric interpretation. This is the book's notation, and if you do the factoring here, to factor out the e to the j omega terms and then have it in terms of positive powers of z if we were doing z, but now we're doing it in terms of e to the j omega in order to do frequency response, this is what you would have. You would have this product of, in the magnitude sense, product of magnitudes that corresponds to a vector going from a pole or zero location to a point on the unit circle, e to the j omega. So thinking back to physics, at least that's how I remember vector notation and so on, if you're viewing in the complex plane as two-dimensional vectors, we have the difference between a point on the unit circle, subtracting from that a pole or a zero location, so that would be a vector that would point from the ck or dk location to a point on the e to the j omega circle. And we'll see a picture of that in the next page. So what the book does is they say, okay, for the magnitude response, this term doesn't do anything. It's just going to be 1. But in terms of the shaping of the frequency response, we have the product of all of these vectors, magnitude, from the numerator, from the zeros, and then in the denominator from the poles. So we'll look at that for a particular example here momentarily. If you want to go ahead and take that over to the phase angle, it will be the angle associated with all of the poles minus the angle associated with all of the zeros minus the sum of the angles associated with the poles to their respective locations. And then from this first term out here, z to the n minus m, with that substitution, that's just a linear phase term. So this is a linear phase term only. So it gets contributed if n does not equal m. That's just a phase ramp that would either go up or down, and then the individual contributions. So an example that the book takes is a single complex zero. I'm going to go look at a little animation, an app that I have in that collection that is not posted on the website right now, but I can post it through Slack if you want me to, if you want to play with it. If you're interested, send me a reminder. The reason why I can't post it is because the files are too big. It's a Windows. This is written in an app, Zojo, that produces standalone applications. So there's pretty good sized dynamic link libraries that support that. So all you got to do is drop it in and you can run it. And actually, since somebody just asked me about it, if I was to go show you what it looks like, the application itself is a couple of meg, but it's all of these libraries that go with it to make it work that get included, and those sum up to more, I guess. Oops, I want to do that. It's got to be more than that. 3.5 meg? Well, I think it's more than that. I'll investigate this, though, but putting it into Slack would be much easier for me because I have it from the old website in a zip package. I can just drop it in there, and then you can get it. But it allows you to play games, is what I like about it. So this is an example where I just placed a pole at 0 by basically saying the denominator doesn't have anything in it, and the numerator has just got a 0 over here at -1, or if I located it there, let's see, I didn't do that right. Yeah, I had that, and then if I move that over, it moves the 0 over here, but I'm going to use it in the way I have it shown here. And this just gives you an idea of the vectors that I was talking about. So as I move around on the unit circle, which is what I'm doing with the mouse, and that blue dot there, we're talking about the ratio of this vector magnitude to this vector magnitude. And that's exactly what's going on right here in the notes. So I guess I should do this too. So it's the magnitude of vector v3 in the notation of the book and v1. And in the book's example, they place the 0 arbitrarily, and then there's a pole at 0. But you can see that if we started off with this as our system, and then we put it in positive powers of z, we have the vector in the numerator here, and then this vector in the denominator is just going from z is equal to 0, because that's where the zero or pole is located, to the unit circle, and its radius is always 1. A simple case. So as we move around, we're having that ratio formed, and if I was to go back to my application right here, in this case, we can get the exact value of the magnitude response, because if we look at what's going on, if the zero's over here and the pole and either the j omega point is right here, what is the distance? We're going the full diameter of the circle, and that's 2, right? Because it's a unit circle. So that's 2, and then the denominator radius is always 1, so it actually doesn't impact anything. But then as I change the angle, or omega, move it around, this is pi over 2. Receiver dropping down. And I guess this is 1.414, right? Is that right? The hypotenuse of a right triangle that has sides of 1 and 1. So this is the geometry idea, where you can actually get a few points, but in this case it really only applies, and I'll talk about this in a few moments here, when you have convenient angles. So I'll take an example of that. But then, obviously, as it moves on around, it's going to eventually be at the 0, and the vector length from the 0 to that point is now very, very small, and as soon as it hits the 0, it goes to 0. And that's why zeros are called zeros. If zeros are on the unit circle, it drives the magnitude response to 0 or tacks it down. In terms of the phase, an interesting that happens, and this is in the notes, but since I've been here, I'll do that. The angle on this, due to the pole, is just linearly increasing from the math, but what's happening, the angle that the 0 makes in the vector that goes from the 0 location to that point, it will suddenly make a jump. And you can see that in the lower plot over here, how it jumps from being 90 degrees to minus 90 degrees all of a sudden. It's at minus 90, and then it will jump suddenly. And that's depicted here. Let's see, getting myself confused. It's depicted right here in that when you go past the 0 that's on the unit circle, you'll have a sudden jump in the angle that's formed, and I have the angles drawn on here. As you go past it, the angle suddenly jumps, if it's on the unit circle. In this case, it changes rapidly, but not a jump, per se. This is another way of visualizing what's going on from geometry, though, in that you've got a 0. In this case, it's just somewhere in the z-plane inside the unit circle, so it looks like a hole, in the sense that this rubbery surface is tied down to height 0 right at that point, and the pole that's at 0 is pushing up to infinity. But we're going around and evaluating on the unit circle, which is going to be a surface that goes up and down. And I show the math here, but this is the interpretation for it, that the 0 is causing the response to go tiny magnitude-wise, or in dB, negative dB, when you hit the angle of the 0, and these are just different angles of the 0, and that sort of thing. I don't have it set up in the software right now for that. I have another app I'll run a little bit later, or maybe I can run them both together. I'll be daring and see if I can run them both together. So I have another app called PZ Tool, and it allows you to place things arbitrarily. But it doesn't allow you to put complex zeros down. They have to be conjugate. So here I've got a 0 down, and I can put it anywhere I want, but I have its conjugate, because that keeps everything real. in terms of the impulse response. This just shows you the frequency response, so I can't move the slider around like I could in the other app. Which was this one. But you can just visualize it as being in there, and if I wanted to pull it in, it would change it wouldn't go to 0, but it wouldn't move the null into the 0 inside the interval 0 to 0.5, like the notes picture is showing you. And this just carries it down to show what the phase looks like. You have a phase inflection when you go through that point where it gets close to the 0, and then the group delay, is being that minus the derivative of the phase, has a negative bump that it gets on it. It's approximately 0, and then it jumps down and comes back up again. The second example that I have here in the notes, taken from the book as well, is putting a 0 right on the unit circle, which is what we were looking at in the software. This just shows you if you put it right up at this location, approximately pi over 2 is the angle of the 0. Then when it sweeps past here, the angle is approximately 2 pi as it comes right up in here, and then as it moves away, the angle switches to pi. So that's the pi jump, and sure enough, that's what this software showed you, right? As I was here, the angle was about minus 90, and then it jumps up by plus 90. So it jumps by pi when you pass the 0 in that location. And that's the type of thing we're seeing here with a single complex 0 on the unit circle. We drive down, kind of like the notch filter that's in the project. Here's the jump of pi, and then here's the group delay spike. Another example I have is a conjugate pole pair, and this is more like a bandpass filter. So just without even looking at the math of it, you can see that if you'll have 2 zeros at 0 if all you do is place 2 poles in the system, convert this to positive powers of z, you'll have a z squared up top, and that will put 2 zeros at 0, right? Because it has to be in equilibrium. At any rate, though, as this moves along and gets close to where the pole location is, the vector in the denominator is going to become very, very short, and the zeros stay at unity all the time. So as you get close to a pole, you get a small denominator vector, and that makes 1 over small be large, and that's the spike. Likewise, when you move to the conjugate location, the same thing happens. This vector to the opposite side is getting longer as you get over here, but it doesn't have as much weight as the small vector in the product, because remember, it will be a product of 2 vectors in the denominator. One will get very small, the other one will just get larger, but this one will get smaller than that one gets larger, so it will give overall a bump, and that's what this picture right here shows. On the rubbery surface that I like to think of, 2 zeros at 0, so it's tacked down firmly at the origin, and then the 2 poles just inside the unit circle are pushing up to infinity. And the analogy I like of this is in a tent. This is what a pole would be. A tent in a camping tent is finite in height, or in a circus tent is finite in height, but mathematically speaking, the pole is a pole that's going up to infinity. But we're staying away from it because we're around on the unit circle. We're not actually where that pole is. The picture maybe is a little bit misleading, but I drew these pictures years ago in Mathematica. This is the software I used. This is just the analytical expression, and for that exact configuration. And I think I might have that one in here. I could put the coefficients in here if I wanted to, but I don't know if I want to do that right now or not. I'm going to go on to this case next. So I'll skip that one for now. So back over here in the notes. The next one is a moving average or comb filter. We looked at this really early on for systems. This is the causal moving average filter. So remember, it takes the present input, samples into the past, a finite window, averages them up. In this case, I'm not dividing by 8. I'm just using 8 total taps. And there would be the magnitude, or there would be the h of z for that system. And remember, this was the roots of unity and that, all that stuff. So when we put that into its surface plot, it ends up looking, my analogies here are pretty face value. It looks like a tree trunk to me. And because I have ponderosa trees in my backyard and I have voles and other animals that like to dig, it's not too uncommon to find little holes, so you could call those gopher holes, right? Those are the points where there's little holes around the trunk. But there's no hole right here at angle 0, and that's the shape when that rises up that forms that pass band. And we know from in the past that it has this comb-like structure where it's got a big main lobe, and then it pulls down to 0, another lobe, and another lobe, and so on and so forth. And all the way along, the phase is purely linear, which is a characteristic of this moving average filter. We'll be discussing linear phase filters towards the end today. So I have that exact configuration in here, and if I turn on the geometry lines, you can just follow the ball around where it's going to be the product of all 4 of these, or 5 actually. Well, it's 5 taps, 4th order. The polynomial is only 4th order, so there's 4. Yeah, there's only 4 active zeros because 1 was canceled out here. So it's the product of all those lengths in the numerator, and then the denominator is just 1. So it just does its thing as it moves around. And then the phase jumps when you're on the negative half of the circle. So I'll extrapolate that a little bit to just give you an idea. We're going to be looking at all-pass filters here very soon, and the all-pass filter we're going to see in the next section here is formed, if it's a causal and stable all-pass filter, all of the poles are inside the unit circle, and then there has to be a corresponding 0 at a conjugate reciprocal location. So this pole's conjugate reciprocal is the 0 sitting out there. So this is 0.8 at an angle, say, 3/4 pi. Then this is going to be at radius 1 over 0.8 at angle 3 pi over 4. And what that does mathematically, and we'll look at this in a bit, if I turn the construction lines back on here, all of these product of the vectors, the numerator are the product of the red lengths and the denominator the product of the green lengths. All of these are staying in perfect check. As we go around, it's holding the gain perfectly flat. And why would you even want to build an all-pass filter? Well, you build it to correct nonlinear phase in other types of filters. And you can be assured then that when you do this, you don't disrupt magnitude response. You're just messing around with the phase with the all-pass filter, and hence introducing group delay too. What filter would you like to see before I move on? This is just, you're familiar with Butterworth and Chebyshev and elliptic filters, so I have low pass, and then I have a couple band pass. Okay, which one? Okay. So turn these guys off. In this case, the band pass is centered at pi over 4, omega equals pi over 4, because it's up here at 90 degrees, and then the conjugate reciprocal is down here. And it's kind of on an elliptical shaped curve. It's not circular, in other words. If I was to take this and fold it up above a copy of it, it would look like they're on an ellipse sitting there at the top. I say that because if I was to look at the Butterworth, which I don't have in bandpass form, but if I was to look at the Butterworth, if it will change for me, which it might not. This thing was giving me problems last night. So I just pushed it too hard. Okay. It'll snap out of it here, hopefully. It did last night that I wasn't running the screencasting software. Either that or out there. It's gone. No problem. I'll start it up again. Problem seems to be in this pull down, where it doesn't want to select it unless I'm very careful with my mouse. And maybe I'll have to back out on this whole thing. I can rebuild this too. I haven't rebuilt it for quite a long time, and I'm running on Windows 11, so I definitely didn't build it to run on Windows 11 with the tool. Okay, there we go. It woke back up again. So now with this Butterworth, the shape of the poles is not so elliptical. It's still scrunched, but it's not as flat looking an ellipse as it is for the Chebyshev. And you can see that looks like a nice Butterworth, nice and flat, and then all of a sudden it rolls off, and then there's a stack of zeros sitting over here. There's 5 zeros sitting at z is equal to -1 to balance the 5 poles that are sitting in there. Now let's go down here. It worked. I have it in dB now. If I was to take it out of dB, you'd see that, but this is more typical of the way you'd see it. So it's just the configuration of the poles and the bandpass filter. Rather than having all the zeros at -1, it has zeros at both z is equal to 1 and +1, an equal number. It's got like 5 at each location, and then you can think of these 5 zeros at each location balancing the 5 zeros up, poles up here and the 5 poles down here. And the configuration of the poles makes it, as you're zooming by, you're passing through the ripple, and the ripple is going to be controlled by the exact placement of the poles. If they're further in and more circular shape, then it has a flat response. You learned this ages ago, right, in circuits? I mean, did you do active filters or passive, or just simply the math?
Still on math.
Okay. Because you can build lumped element filters for these. Okay. We do that in the COM lab. I have experiments in there that are chip components on a PCB, and they characterize that with a network analyzer. So it's interesting, though. To me, it was interesting writing this all out. But the geometry idea, let's take that one step further. Let's close this. And a problem that I could do, I don't believe I put a problem like this on, I did not put a problem like this on the exam, but it might be in the final exam. So an example of what the geometry can do for you is In terms of a simple calculation, you can't do a whole lot. And we have tools like Python, MATLAB, and Julia, so we don't really have to rely on that a whole lot. So suppose we have this configuration, and let's just suppose it looks like that. So it's stable, it's going to be causal, we have two poles on the unit circle, and then we have one at, I could say, minus 0.8, and how would we get the magnitude response? We can, if we wanted to get just a few points, we can't get the points in between, but if we go with points at 0, say pi over 2 and pi, we can do that with simple geometry. So we can go, if we wanted to be at this point right here, we're just talking about drawing two vectors in there and drawing two vectors in there. So in terms of our response, we have, just looking at the picture up here, the 0 up on top to the origin, that will be square root of 2, right? Because it's the hypotenuse of that simple triangle. Then we have two of those, because we have the hypotenuse on the bottom. And then in the denominator, we have the vector that runs from minus 0.8 to plus 1, so that's going to be 1.8. And then the one that's at the origin is just 1. So that's how you could get that would give you the DC gain then of the system for this particular configuration. And if I wanted to take another example, now I'm going to see if I can do this. Okay. Amazing. It deleted everything that I wanted and nothing else. So now I'm going to be sitting up here at pi over 2, and I can go ahead and do that calculation, but it's not going to be very exciting. I'm going to have a line connecting across, there, and there. If I pulled the zeros in from the unit circle, then it would be a little bit more exciting, but still, let's write down what the magnitude numbers are. So in the numerator, we have a 0, since we're sitting right at it, and then we have a 2 for the 0 that's across the way. And then in the denominator, we've got the hypotenuse of a triangle that has a base of 0.8 and a height of 1, so that's going to be the square root of 0.8 squared plus 1 squared, and then the pole at z is equal to 0 will just be magnitude of 1. So the answer will be 0. But if it wasn't poles on the unit circle, then we'd have a numerical value other than 0. And you see how this would work then, right? You just have, this would not be 0, it would be something else. I picked something that was really easy, but it just gives you an idea, and then you can fill some points in. This was a method that is talked about in the book and has been in other books, and I know is in undergraduate linear systems theory courses. With the tools that we have today, we just, can drop things into Python and get it immediately. So it's not that big of a deal. I think I do have some examples in Python though. So if I was to just go look in the notebook that I have for this chapter, I have some group delay stuff in here. Then I have a section in the notebook called geometric evaluation. So here I took an example that was a little bit different than the one I was doing. In this example, I've got a system that has 3 zeros in it and then 3 poles at 0. So I took all 3 of those zeros and convolved them together in Python to create a polynomial. So I convolved the 0 that's at 1 minus j 1.2, and that's this one down here, and then I convolved that with the one that's on the top, and then I convolved that convolution with the 0 that's over here at 0.9. And then I had a1 equal to 1. I create the pole 0 plot, and then I could go ahead and analyze that if I wanted to. I don't know what happened to the rest of my notebook. Something's freaking out here. Seems like something's missing. I don't think I'm really going to go into it. It looks to me like I lost my notebook though. So I'll restart my kernel, and it might be because I did something crazy last night. Jupyter down here in the lower right was telling me that there's a new version out there. So I went and installed it. I probably should have never done that because I think I maybe have lost everything here. So I'm going to go close this. This is chapter 5. Close that. Close the kernel for chapter 5. This is an older version of the notebook, so it's not the one I wanted. Okay, this is what I had from 2 years ago, and this is where I upgraded chapter 5. See, I lost contact with it because it says I last updated it 11 hours ago. That would have been last night when before I went to bed. So let's see if this comes back at least. Okay, there's pole 0 plot. And then after I did that, just checking that I can do the calculation of the geometrical calculations. Python has a function called norm, and it can find the hypotenuse or the magnitude squared just by doing it that way. And I just, for the fun of it, I brought in the linear algebra package to do that. So I just applied that to the problem geometry of getting the magnitudes of all of those zeros in the numerator as this calculation, and the denominator was 0. So there that is. And then what I can do to really speed things along, I can go into freq z and I can say, suppose I would like to get the magnitude at 0 and at 2 pi times 0.25, which would be at pi over 2, and then at 2 pi times 0.5, which is at pi. So I'd be going back to kind of like what I sketched out on the paper, where I'd be putting my dot here to get the magnitude there, putting it right up here to get the magnitude, and then putting it right over here to get the magnitude, those 3 locations. So what I did in Python, as I just said, use freq z, just evaluate those 3 points of my rational system function, and it just gives me the number immediately. So I get 4.636 at 0, 0.591, and 0.244. And of course, I could sweep that around and get the full plot if I wanted to, and that's probably what I would do normally. But if you were working a problem, you could check it, or just simply see how you could work it with the more modern tools. The geometry idea, though, is still something that I may throw in on the final. I don't know. It'll just be something that, remember, it's open book, open notes, but you can't use a computer on the final. There was another example in here. This was bandpass resonator. It just puts 2 zeros up, one up minus 1, one up plus 1, and then it puts a complex conjugate pair up. And this one is, the geometry intuition on this one is pretty nice, because it says that if you wanted to build a bandpass filter, a very minimal bandpass filter, you would for sure say, I don't want to pass at DC, and I don't want to pass at pi over 2, or at pi, I mean, but I'll put this conjugate pair of poles up, and I can control the radius of these poles, and then as I cruise around and go past that guy, I will peak up and get a nice response. And for that, I can go over to this tool. I can't do the geometry thing, but I can leave it exactly as I have this. I can put down a pole pair. I'll delete that pair, and I think I want to delete, yeah, that one. So automatically, in the way that I wrote my software, it's, I guess it needs another 0 right here, which I don't think it's going to put in by itself, so I can put that in. These are the coefficients of the polynomial, so it did what I wanted to do. And now what I can do is I can move that to some radius. I'll put it in dB, and then you can see how it indeed is peaking up at that point. And I can, of course, move this around. And the better way to do this filter, though, like the resonator example said, put one of the zeros out over here, and these are a complex conjugate pair. So let's remove those. Put one there. Put one right over there. If you remember the picture in the notes here, this is exactly what it was doing. It said, put a complex conjugate pair up to give you the peak of the bandpass, and then to make sense from a bandpass standpoint, I want to pull it down to 0 at 0 frequency and pull it down to 0 at pi frequency. Does that make sense? It's like if I put the zeros in the middle here, it don't have as much impact. I'm not pulling it down as tightly to get the better response, and that's what we're seeing right in here. It's pulled down very tightly, and of course now when I move these around, you can see what's going on. If I move it close to the unit circle, and I can gain scale in this thing too with the roller bar, but just get the idea that, yeah, I can't touch the unit circle because then I'm unstable, right? The region of convergence is the exterior of the circle of that pole radius, and as long as it includes the unit circle, I'm stable. For whatever reason, I just lost my mouse control. I can't pull it in. Now, Yeah, something weird is going on here. Yeah, it's acting like there's complex zeros, or poles, I mean. When I first wrote this, I thought it was really cool, and I worked really hard on it to do GUI stuff and drag and drop with the mouse and moving. I learned a huge amount of stuff, but it was entertaining mostly for me. The other thing I guess we could look at, though, is the fact that in this system we get, if the pole is pulled in more, we get not so sharp of a response, but the phase is also a very gradual transition. So the derivative right at this point is going to, minus the derivative will be the group delay. The group delay won't be too much, but then as we move this in tighter to get the tighter bandpass peak, this is a fairly good peak, then the phase is making a more rapid transition, and it's going to create a bigger blob at the point where the peak is, and that's depicted right here from the analysis. There's the magnitude, there's the phase. My software doesn't show you the group delay, but that's just showing that this peak is going to get bigger and sharper and become more of a group delay annoyance right in the vicinity of the signal that you're trying to pass. If you're not worried about group delay, you could do this, but it's not advisable for a lot of the modern digital comm systems where you'd want to have linear phase. So any questions on that? You're an audience of one. I wish more people would have come today. I pushed Slack info out last night, but it is what it is. So now we're going to enter something that's very interesting, something that should be totally new and different. And that's the relationship between magnitude and phase. And it sets a stage for everything else that happens to the very end of the chapter and all the topics that are in the problems and on the exam. It says if the magnitude response is known and the number of poles and zeros is known, then there's just a finite number of choices for the phase. Flipping it around, if the phase response is known and the number of poles and zeros is known, then to within a scale factor, there's a finite number of choices for the magnitude response. And this doesn't seem all that amazing, but it's just telling you that in stable and causal systems, you just have so many choices if you've got so many poles to put down and so many zeros to put down. And I guess being that in the system I'm working on in my work, I had to come up with a filter for a transmitter that has to shape a spectrum so that it meets the NTIA spectral mask for SATCOM. So I wanted it to be linear phase, and I wanted the complexity to be minimized so that it could be implemented in FPGA. And my boss said, try one of these, because it's worked before for me. So I ended up taking his idea and then basically tuning the design to work exactly for the needs of this project. And the FPGA people are beginning to test it right now, and I'm looking forward to it working exactly as advertised in the FPGA. At issue is I did a floating point model, they're doing a fixed point model, so that's what has to happen. And it's also a multiplier-less filter. It's a filter that does not require any multiplications or divisions, so that's very nice for the DSP as well. It does just additions and bit shifting. So scaling is done by shifting right. You remember that from somewhere in microcontrollers or something, just right shifting. Right shifting is like a great thing. Divide by 2. It's too much work to do an actual division most of the time, but you can divide by 2 by right shifting, and that's used a lot in real-time implementations. So getting into this statement and trying to understand the relationship between the poles and zeros it starts by saying, let's look at the magnitude squared response of h of e to the j omega. But before we do that, let's just back up and consider that before we make the substitution, z is equal to e to the j omega, we can look at it in the z domain, and that would be h of z times h conjugate of 1 over z conjugate, and that's one of those somewhat more obscure properties in the z transform domain, that if you conjugate something, it becomes this in the z domain, the 1 over z conjugate. This is an important part in making all this point, but putting the system up as having poles and zeros in it, and as an exact formulation, that's what we have right here. So we have, in the original system, we would have had those zeros and these poles, and now in our H conjugate system, we have these zeros and these poles. And all of these show a character, and we'll see it more on the next page. CK would be a 0, and then over here, CK conjugate, and the fact that it's written with a positive power of z, if we factor the z out of that term right there to make it look like something that would make more sense to us, or if we flip the other term, that's probably easier. So this has a 0 at 0, and then this is this 0 is 1 over CK conjugate, or 1 over, yeah. So when you take a complex number and you want to do the reciprocal of it, but if you want it to lie in the same radio, if you just take 1 over CK, you will get the angle will be in the wrong location, but if you conjugate, then you'll bring it to the right location. So these two zeros sit across the unit circle from each other. And the poles do the same thing. So if one pole or 0 is inside the unit circle, then the other is outside the unit circle in the same angle. So that's this picture. The poles are unique because for the system to be causal and stable, we have to view the poles as being the ones that are inside the unit circle. But the zeros are not unique. Once we're looking at this C of Z system, it's somewhat confusing, but you know, these two are together. And then just another example, these two are together. That one has to be picked because if we want to realize this system, we have to do that. But if we wanted to realize a different system that has the same magnitude response, say for this one, we could go with that 0 or that 0. It doesn't matter. It'll be the same magnitude response, because that's what we were doing here. We could swap them around in the system model for C of Z, and it wouldn't change. So this is kind of the interesting thing that comes out of this. And why does this matter? Well, it says that you can synthesize different systems and play some games with the all-pass filters. And I'm going to give you front row seat in the exam. You have a neat problem in there. And I'll go through that later. I'm going to save that stuff for the very end because hopefully more people will be here for that. But there's some really nice examples in the Jupyter Notebook as well of going through this for building an equalizer. And that comes up a little bit later here. So first off, we have this representation where we have poles and zeros that are conjugate reciprocal locations for both the poles and the zeros. So we just have 2 of each, always lined up in a conjugate reciprocal location. And this just shows you how many cases we can make with the 4 zeros that we have in the system. We can make the zeros all inside the unit circle with the poles, and then that's the one at the top. That's called minimum phase, and that'll be a definition here that follows this. Minimum phase system has all its poles and zeros inside the unit circle, and there's some homework problems on that, and I think there's one on the exam on this too. Maximum phase takes things to the other extreme, and it says we have to keep all the poles inside, but we'll put all the zeros on the outside locations, and then that will create the maximum phase system. And then 2 and 3 are the mixtures of those for this particular situation. The magnitude response does not change, and the phase response does change when we do this arrangement. So we're just looking at other configurations. And like I said, the exam problem will look at one extreme, and there's an example that goes with that exam problem that's right here in the notes and is talked about in the Jupyter notebook, already worked out in there, of how this can come up in reality. Let me just give you a quick physical understanding of how this can happen, and then it'll be in the back of your head when I come to it. We're looking at terrestrial communications, mobile radio, cellular in particular. If I'm standing here and I'm receiving a signal from a tower, let's suppose it's the towers up here, I'm AT&T on my phone, but I don't remember what towers those are. Who owns those? Does anybody know? Is that AT&T? I think there's more than one cell provider up there anyway. At any rate, so suppose there's a two-ray path. Generally, there's many paths, but suppose the dominant paths are, there's 2 dominant paths coming from there, but I don't have a direct line of sight path because I have obstacles in the way. So I'm going to rely on reflections off of something. So what can happen is, normally you'd think in a line of sight communications, like the Cheyenne Mountain down there, if I was getting a radio signal, I would get the line of sight to me would be the shortest path. The longer path would be one that would go to some peak, maybe it's Blodgett Peak or some one of those that's further north, and then it would reflect and come down to me. So that would take more time to get to me because it's a longer path, and there'd be more path loss because there's 1 over distance squared path loss, divergence of the rays and of the wave. But in cellular, with obstacles and things, the shorter path might be the weaker path, and the stronger path might be the longer path. And then that will create a situation of a zero, and I'll show that here in a little bit, is outside the unit circle. So it becomes non-minimum phase mobile radio channel. And you say to yourself, why did this happen to me? Well, it did. Now I want to try to equalize it. So it can be done. And not perfectly, but it's something that can be dealt with. Most SATCOM systems wouldn't have that problem. They'd just be a line of sight from the satellite, and maybe it reflects off of some nearby objects before it gets to you, and that would be still the minimum phase situation. But mobile radio is a totally different game because I'm looking at the building behind us. The radio wave's not going to go through that building very effectively. It's going to be decayed a lot, just like the signal going up through here to get to that tower. It might be a better thing to be reflecting off of the building behind me and coming in through the window or something. I don't know. Have you both heard of ray tracing? Ray tracing is in gaming and other things for good geometry and game playing. I know they use ray tracing engines for all these things. My sons play video games a lot. They're older, but they play them every weekend when they're both come home to visit us. But ray tracing to me is a means to trace radio waves and look at propagation phenomena. It's very, it's pretty exciting. I had a course on that that had some ray tracing examples in it. It's not back up on the website again, but there's software tools out there that can do the ray tracing analysis for radio channels. And it can trace all the geometrical paths and then put in reflection and attenuation, remember things in fields and ways for transmission, reflection, diffraction, and do all that stuff. People do that for difficult scenarios. They model like that. So what we're going to do to get into this more, we're going to see how are these systems related, the minimum and maximum phase systems and all the other ones that were talked about right here, all give the same magnitude response. So the all-pass filter, which has a constant magnitude response, is going to be the key to relating them to each other. So suppose h of z contains a factor of this form, a z to the minus 1 minus a conjugate over 1 minus a z to the minus 1. So I've just done some factoring on this. So I pulled out the minus a conjugate, and now it looks like I have a 0 at 1 over a conjugate and a pole at a. So this is an all-pass section, and then this gain factor just comes in order to get the ratio to make the most sense to us. So if I go ahead and look at what's going on the unit circle, which would be the frequency response, I do this factoring, and I can do the factoring that I have here and see that the numerator and denominator are just conjugates of each other, and that's really just this form right down in here. When we're doing modeling here in an example problem that comes up fairly soon, this is the type of thing you end up playing, and then those gain factors come flying out, and those show up in the one of the homework problems for sure. But this is just proving that this original form is indeed in magnitude. It's just this over this, and they're conjugates of each other, so their magnitudes are equal. And I had to factor out an e to the minus j omega, but that has magnitude of 1. So this is an all-pass factor. And if you look at the way this can happen, is any number of all-pass factors could show up in a system and not ever alter the magnitude response, but they do change the phase response. And like I hinted at but didn't say very early in the class, you can use an all-pass filter to modify the group delay. So one of the big things about filters in general is we're just looking at the bandpass filter. If that was a group delay and it peaked up right there, what we could do is we could put an all-pass filter in somewhere or another, so that we're hopefully we're going to get a flatter group delay response. So the all-pass filter would try to put some group delay in at lower frequencies and put some group delay in at higher frequencies, so that in the band of frequencies of interest for the bandpass filter, at least we flattened the group delay. Not made it go away entirely, but for the band of interest, we'd made it flatter. And group delay is additive. When you cascade systems, you can't make group delay negative except under certain mathematical modeling concepts, which to me is still like a mystery, but I'm not going to go down that path right now. But so what you have to do, if you have to get rid of a blob of group delay that's some positive value, you can compensate by adding some all-pass sections in to bring this group delay up so that it can manage that, and then bring it up here to make it flat in the pass band. Do I ever have to do this with digital filters? Not really, but I know that in filters that are on SATCOM systems, they would be cavity-based microwave filters. They have done things like this. They've been doing it for ages and ages. A cavity filter won't necessarily be, it'll be low loss, an efficient filter, but it won't have constant group delay, so they can equalize them in the design using cavity filter design techniques. But in DSP, you can also, of course, equalize things too for group delay. So taking the all-pass idea up to a higher order, an arbitrary order all-pass, this would be an nth order all-pass. this is, in the blue box, is what it comes down to. And the way I remember it is, I remember it for the case of the real all-pass, not the general complex one, but this, the memorable thing about it is the denominator of the coefficients are, this is essentially A0 is 1, A1 up to AN, and then up here in the numerator, there's a c to the minus n that was factored out, but you could visualize this as being flipped around the other way, so the coefficients count up, and then they count down in the numerator if you just do that flipping. And I have that in Jupyter for sure. Next section here in the notebook that we're looking at. So this just takes the first order case. All I did was slap down numerator and denominator. I just said minus 1/2, 0.8, and 1. And then I said 1, 0.8, and minus 1/2. And the property that I get that makes it an all-pass filter, it's just like we were looking at the very beginning. This pole and this zero are conjugate reciprocals of each other. Likewise, that one and that one. That's just a property of the all-pass filter. And we looked at the pole zero geometry thing earlier. We saw that as well. I guess I'll bring that up again since I didn't really study that one because it was crashing on me. There we go. So these coefficients, you can see in this example, are running in the opposite order. And then here's the gain. And then I'm just going to move. Remember, we were doing the geometry earlier. So I interact with the very first pole zero reciprocal setup. And there, of course, there's multiples in here, but no matter where I go, everything is just held in check. The gain is perfectly flat. Is that interesting? To me, it's very cool that things work out that way.
Are you moving around?
This blue point, we talked about this before you got here a lot. I was demoing this a lot. This is just a point on the unit circle, and this was for pole zero geometry studies that we were doing earlier. So this, it's the ratio of the product of the numerator vectors, all the red ones, divided by the product of all the green ones that forms the pole zero geometry understanding. We did a little example on a sheet of paper too, that's in the notes now too. But this just drives this idea home very clearly that the phase is getting messed around with a lot, but the gain is perfectly flat. The other thing I demoed before you got here was PZ tool, which lets you approximate things. So here, I could take that one, and then I'll remove those two zeros that I put on here, but then I'll add a conjugate zero pair. It keeps adding things in because it's trying to keep things in equilibrium, but now I have the setup for an all-pass. I have these two, which I can adjust, and then I can take these, and if I try to get the magnitude in over here, if I can do this, this is a little bit tricky. You have to visualize where's that going to be. I'll maybe put it out there. Let's put it in dV. It'll be easier to get it flatter. I just can't, I'm not good. This is my style of a video game, though. Move something around. But that's the idea. Does that make sense? And there's the phase. And I could put up another one, too. I could add another one. And in my software, notice, because I'm only doing magnitude response, I can put poles outside the unit circle because I can think of this as being anti-causal. mathematically implemented, but I know I'm not going to build a real-time causal system, so I'd have to do that. I could do that. I could put another one of these over here and try to drive for the same thing, probably in this sense. But I know I don't have to play games like that. I can just make those coefficients you see up there, if I just made them all match the opposite order of what's in the denominator, then it would be perfect, because that's what we were just looking at. This is just a side effect of this. And MATLAB used to have a tool like this ages and ages ago. I don't know if it's buried inside of MATLAB, but I don't care. I don't really care about it in Python. I could make GUI sliders for Python, but this was an app I created a long time ago to learn about GUI programming and interactivity. This also has this little feature here, so you can see where the poles and zeros are in magnitude and phase form, or real and imaginary part. I'm trying to remember when I did that, but my very first sabbatical was when Microsoft's Real Basic came out. My sons were home from the NICU at Memorial Hospital because they were preemies. They were born at, 28 weeks or 27 weeks. They were really small. Their fingernails were the size of a pencil lead, and they were on oxygen and heart rate monitors. So my wife had to go back to work, and one of the things I did in my sabbatical is Visual Basic came out then, so I sat down and started learning it, and then I got more and more interested in it. But then I didn't do anything for a while after that, and then I picked up another language called Real Basic, which is now called Zojo, and that's when I got serious about the object-oriented programming in Real Basic, which is very similar to what Visual Basic started out as in terms of how the language syntax worked. But Basic sounds really crude and old-fashioned. You might have learned it a long time ago or bumped into it. This is a much more sophisticated version, and it's typed and everything like that. You just don't put down variables and add numbers. You have to declare a type just like you would in C. And you can have arrays, you can have complex. I actually highlighted, the way I developed my app here is somebody wrote a library, open source library called Complex Matrix, and I added that to my development. So I had a bunch of capabilities for doing things with complex numbers, not just matrices, but arrays, and I think some other things. These are some of the libraries that got put into this when it was built a long time ago. 2015 was the last time that was built, so I haven't built it lately. I do have the source code, but I don't know if I'd have any issues trying to build it right now. At any rate, what did I have in here? Oops, don't want that. So I went on and did some higher order designs in here too. I don't think I really need to look at all of those yet. I have magnitude and phase and group delay plots all the way through here, though. I'll save that for another example. I also have some hints in here for text problem 521. This is actually really good. I would consider taking a look at it. This is the PDF version of that, so I can look at it in here. Here's your notch filter, too, that is in the project in two different places. It's problem 3, and it shows up, no, it's problem 4 is the focus of this notch filter, and then problem 5, the real time, is where the notch filter is used to null out the jammers. Did anybody get that working?
I got problem 4 done.
Okay.
Working on 5 right now.
Okay. There's a geometric evaluation thing, but I have the LPass in here. So this is what we just went through We were just looking at this basic example. Hey, it didn't work. It died even earlier. Notice the ceiling up there? They plugged it into a different outlet for me, but it didn't solve the problem. Now it's going to come back up again. I had to come back to be a professor for one semester, and I had to get involved in trying to solve a terrible problem that apparently Dr. Kelker confessed to me last week that he has had that happen in this classroom, and he assumed that his computer was bad, and he didn't say a word to anybody. I don't know whether Dr. Song raised an issue, but engineers can be really introverted, right? And I think we are by nature, because that's just kind of goes together with being an engineer. But you think I'm wrong, nobody, it must be me, it's not, but I'm convinced it's not me, it's something else. At any rate, we're back up again, and I'll report this to Dr. Tromboli before I leave today. So here I just use some functions that can be helpful in looking at homework problems. I put up this higher order all pass, and I have a function built in to the IIR, or the IIR filtering package, and it's also in the FIR filtering package. I think I loaded it in somewhere up in here. I know I may have pointed it out to you, and it's in the exam too. Let's see, where is it? Up here. I guess before I studied the notch filter, I loaded it in. So I'm thinking it's right. There it is. So IIR Design Helper and FIR Design Helper both have this function in them that allows you to overlay multiple filters. So if I have multiple B arrays and A arrays, I can put them in a list in Python, which is just the square bracket, and then it will plot all the filters on top of each other just like that. You don't have to do that much work at all. It'll just plot it out for you. So that's magnitude. And then you can do phase and group delay just by changing it. So I did that here in this all pass example, which is way down the page now. So here it is right here. And then I just did the frequency response list, this one just for a single filter though. So I have once for dB, once for phase, and once for group delay. So there's phase, and there's group delay. Group delay looks fairly ugly, but that just shows you that the all-pass filter can be a means of compensating. And then these primitives for simulation just carry you through doing a design of a filter and then trying to model it. I don't think I really want to go into that with the time constraints for today, but take a look at it. If you're working problem 521, you can work it without any Python if you're good at sketching and visualizing what's going on with the multi-rate processing and so on, but this gives you a means to cross-check things. And when my solutions go up eventually, you'll see how I used this basic approach. This was sort of the primitive approach that primitives in software I came up with for filtering. Actually, I take one of the problems, I believe, right in here. There's my triangle wave spectrum. And then I look at what happens here when I downsample. Yeah, that's not the one. Okay, just filtering it directly. Then here, I'm going to downsample by 2. And when you downsample by 2, you can see that the bandwidth doubles when you downsample. And that's one of the, I think that's one of the problems. So we're going to go into linear phase. Probably going to take the break. I'm going to wrap up the all-pass idea, though, with here's the discussion of group delay compensators. It just shows the math of what the group delay looks like. But then we're going to go into minimum phase systems, and we'll do this after the break, and then we'll be into some examples, which is similar to one of the homework problems, and then this example here of the equalizer frequency response compensation, and this example that's in here is converted to an application example in exam 2. So I want to spend time on this. And then it will be on to linear phase filter design, and then that's will be the end of the chapter. So I'm on a fine timeline because I have to do all of that, plus I want to go through hints to the exam since it's already up there. So come back. If you can come back in 10 minutes, that would be nicer still. We'll see if the projector manages to just stay running the rest of the time. Okay, so we're back from the break. We're going to go look a little bit more at some more definitions. But first off, we've come through the all-pass filters. We started out with the mixing and matching of poles and zeros to get different systems that have the same magnitude response but maybe a different phase response. Remember, that motivated the idea that how are these interrelated? Well, they're interrelated through an all-pass filter, which just moves a zero and a pole. So now we're going to get into the idea of the minimum phase system itself and dwell on it. And this is kind of a base point. A lot of nice properties come when you have a minimum phase system, and that's what you desire to have. And fundamentally, for any system, H of Z, you can write it as a minimum phase system in cascade with an all-pass system. And that just gets back to what we started before the break. So it's understanding how that works, and then that builds into some homework problems. And then the next thing will be, that comes up at the end of the chapter, will be any system can also be built as a minimum phase and a linear phase system in cascade. That's just another twist on the idea. And all of this stuff requires you thinking in terms of poles and zeros. So before I even get going here, let me make sure I still got that up. I don't have it up, but I'll get it up. It's in the section here. I have links in the exam, for example, but I have a link in course materials. It's that link right here. So you can see what the game is here, and this is we're heading towards this right now, but the game will be, we start off with any system. We're first looking at how you can decompose it into a minimum phase and an all-pass system, and then how you can decompose it into a minimum phase and a linear phase system. And this is the last topic, what is a linear phase system? So considering the time and considering what I have to do, I need all the time I can get, but this makes it sound like, hey, at the top level, there's just some understanding to get going on both of these. And they both can be done very simplistically in terms of pole and zero plots. You can sketch it out on a sheet of paper. If you have to actually do the math part of it, which that takes a little bit more time, it's a little bit more tedious, that's in the homework, and will also be on the exam problem, exam 2 problem. But on the final, typically I put a problem kind of like this, where all you have to do is draw these pictures, and you just have to know what you're doing. And that's the thing. For a 2-year-old to say, I'm going to draw some circles and put some X's and O's on it. I'm not playing tic-tac-toe, and I'm doing a little bit more than that. But there's a lot of power in just knowing what you're doing with poles and zeros. So that's where we're headed. So very simply, though, a non-minimum phase system can always be made into a minimum phase system, and all you have to do is reflect all the zeros that are outside the unit circle to their conjugate reciprocal locations inside the unit circle. And the converse is also possible. So to see how this works, if we have H of Z is composed of H1 of Z, which is assumed to be minimum phase, and then it has this 1, 0 in it up there, which is going to be outside the unit circle. It says where Z is 1 over C conjugate and magnitude of C is less than 1, so that's got a 0 outside. We can find the minimum phase equivalent, and the way you can write this down is I can just take the system as defined up above and then to convert it to its minimum phase equivalent, I'm just going to cascade it with the all-pass filter. So the all-pass filter will take care of doing that conversion for us. In this case, H1 of Z times this is minimum phase, and it's related to H of Z via that all-pass section. So which one is minimum, which one's not minimum phase, maybe it's kind of arbitrary, but that's what's going on here. So if I'm getting you confused, it's because I'm getting confused thinking about which one is which in this case. It's best to just look at an example. This will make it clear. This is the mathematical viewpoint of it, though. Let's just show you how clear it is on paper. Pictures, I mean. Oops. So if this is the original system has a pole inside the unit circle. It has a 0 outside the unit circle. So how do I make that minimum phase? I have to take the 0 in that H of Z and move it inside. So I want that 0 that's outside to be flipped inside. So I just take the conjugate reciprocal of that location. Suppose that was at 1.5 on the real axis. The reciprocal of that is 1 over 1.5, right? So it's going to be right in here, or whatever the number happens to be. And then how do we relate the two together? If we have this minimum phase system and we cascade it with the all-pass system, that's going to do it for us, because when this cascades, that pole is going to annihilate that 0, and then we're back with this 0. So we'll have the 0 that we started with and the pole that we never touched. Does that make sense? Wonderful, right? I'll tell you right now, the last 2 chapters that we're going to be zooming through after Thanksgiving are going to be stuff like this. It's not going to be nearly as complicated. It's going to be more conceptual and just visualizing things.
So in that one, the 0 for the all-pass, it goes back to its original position, and the pole takes the place of the 0 in the minimum phase?
No. This pole here that we added in this all-pass system just goes away.
Okay.
If all we wanted to do was say H of Z and H minimum of Z are related, they're related because of this all-pass section. Okay. That's all we're doing. We're just saying we can do it that way. Now, what we can't do in a realizable system is we can't make this all-pass system be flipped where the pole is outside and the 0 is inside, because then we would have a pole outside the unit circle, and then the region of convergence is exterior to the unit circle, and then we're not stable anymore. Remember, we introduced that idea a long time ago. You do have to, in order to play the game, any game for that matter, I was dealing with an issue that involved my credit card and a thing I disputed. It turned into a mess. It's spun out of control right now, where a collection agency is after me for some money, and I had to learn how to play the game that they don't settle things for 90 days after the event, and it still hasn't gone through 90 days yet. So it's really weird, but I told my wife, I said, I'm learning how to play the game because it is a game in a sense. So this game here is you do have to know what you're doing. If you just throw your arms up in the air, you're going to get it wrong every time. You're not going to make sense out of it. But if you visualize what's here as a cascade, this system and cascade with this system means we're multiplying the system functions, so that'll happen. And we learned that a long time ago, right? Pole 0 cancellation can happen. So going back over here to the notes. So in this case, this is the system, and we want to find the minimum phase version of this H of Z. So you look at this system, and this is an example in the book. you see that that's radius 3/2 and 3/2 at conjugate location. So that's the issue. That's what's keeping it from being minimum phase. So what we have to do is take this system, and this is the mathematical view of it. The picture view is easy. We're just going to build 2 all-pass filters, but we're going to see how this extra gain, we're going to see how this comes about. So what we do is you look at factoring. So you factor out these 2 zeros that are outside the unit circle, and when you do that, you have 3/2 times e to the minus j pi over 4 and 3/2 times e to the j pi over 4. Those 2 exponentials go away, so you just get this 3/2 squared, and now you're left with this configuration, and this looks like part of an all-pass filter at this point. This has been untouched. We're not going to move that, but this is part of an all-pass filter that has the zeros inside the unit circle, and then we just need to lay up against that the all-pass filter, which is in the second line down here, that has the zeros in there and then has the poles in it, and then we have the conjugate reciprocal thing going on there. So this right here is now the minimum phase. That's the all-pass. So the decomposition is done. The quirky thing that comes out of this, though, is that this was our original system, but when we want to write it as a cascade, we have to do this factoring. So this 9/4 is going to now be attached to the minimum phase system, because the all-pass system is going to be constant gain, but depending upon how it's defined, it's not necessarily unity gain. It can be a constant at some other value. So this has to come out of here as part of the decomposition. So now we have kind of like that picture I was just showing you in the other notes, where we started off with h of z has those 2 zeros outside the unit circle, so we reflect them in to the inside over here. We leave the 2 poles that we started with untouched, the one at 0, which balances one of these 2 zeros, and then the other pole on the real axes. And then we design the all-pass system that has the poles inside to replace those zeros with, or to allow us to move the zeros to inside the unit circle. So this times that gives it the original, but if we just want to focus on the minimum phase, it's just this, which is related to the original through this. You don't necessarily need this, but this is just sort of what you see as how they're connected to each other. This is going to be constant amplitude and messes with the phase only. So now we'll go into something that helps out with the exam problem, frequency response compensation. So we have, if we have a minimum phase system, that means it's stable and it has a causal inverse. We talked about inverse systems last time. Remember, the inverse system is just taking the system, flipping it over, but we had to have both poles and zeros inside the unit circle, otherwise it would bounce out to be something with a pole outside the unit circle. So what you can do is you can take a non-minimum phase system and phase compensate it with the all-pass filter to make it a minimum phase system. That way we can take that phase compensated system and we can invert it because it will have poles and zeros inside the unit circle. So in this case, this is the book's notation again. We have a distorting system like the radio channel I was talking about before break, and we build a compensating system that is going to try to remove the amplitude distortion introduced by the channel. So what's going to happen in this case, which is a little bit different twist, is because we end up using the all-pass filter to make a non-minimum phase system minimum phases, when we get done building the compensator, we'll be left with the all-pass response. So the system is equalized to the point of being a constant amplitude response, but it will have an all-pass filter remaining in it, which means it has some phase distortion, but the amplitude distortion is resolved. Does that sound reasonable? Or am I stretching your brains up too much? This is what you are faced with, though, in a mobile radio channel situation, and it's been dealt with in our handsets for years and years and years, where they can build equalization. Earlier generations of cellular telephony used a training pattern called a mid-amble. It was packetized so that bursts of RF would go off from your handset to the base station. It was time division multiple access, so you had a slot that you would transmit in and receive in. Somebody else with a cell phone on the same network would have a different slot they would transmit up and receive, and so on. There would be like end users on the same network, same sector of the same cell tower, actually. And in that burst, in the middle of that burst, there was a training pattern that would be a known sequence of ones and zeros or bits. And then at the receiver at either end, they could analyze that inside the handset and see what is going on distortion-wise and figure out what the channel is. So they could figure out, hopefully you can believe me when I say this, you can figure out exactly what the H of Z is of that channel. And it will, if it's not minimum phase, they're still going to try to clean it up with a compensating system like this, knowing that known mid-amble pattern. And things like this get used all the time in comm systems, training sequences. It reduces the overhead because the number of bits sent through the link is less, that are usable to the customer are less than the total capacity, but it's considered to be a necessity. I mean, synchronization and other things have to happen as a rule too, so they try to maximize that. I mean, maximize the utility out of that added overhead in a system. I don't think anybody can work without synchronization in the digital world. Our brains are powerful. They can work. Whether or not you're far away and it takes a long time to get to me, I can still decipher a digital system. It has to understand how to sync up. So here's an example where there's 4 zeros entirely, so it's a complete FIR. Think of this as a radio channel that would have multiple rays in it. And this one is minimum phase already because the zeros are inside the unit circle, and that one's maximum phase. They're both outside. So we could draw this picture if we were doing a different homework problem, but the basic problem is we're going to use an all-pass filter to represent the transformation of this into the minimum phase, or to relate the minimum phase equivalent, which would be that, and then we could go back to that, right, by having that's what the all-pass would look like to convert from the minimum phase back to the all-pass. So this is our system model, and of course the inverse of this is going to be that all-pass. And this is a little bit bizarre, but that all-pass is going to be minimum. It's still going to be realizable. Because if we take the all-pass and flip it over, then, no, the all-pass will be realizable. Just leave it like that. So this is our original system, non-minimum phase, distorting system. Notice it's got a lot of fluctuation in the amplitude response, and then magnitude or phase and group delay. Go through this exercise. In this case, we end up with a factor kind of like we did in the previous example. And this is now the distorting system minimum phase equivalent. It's got a different phase response. It still has the same magnitude response. So we build the all-pass system that relates to the two. It's sitting right here. We have to use the minimum phase inverse, and this is what the all-pass compensating system effectively looks like. And then, well, this is what is left over after we compensate. So we end up with perfectly flat gain overall. We'll end up with this phase and that group delay as a result of building this equalizer. And you're going to try this out on a digital comm link, a very simple one, and I'm holding I hold your hand all the way through it in exam 2. So properties of minimum phase systems, a lot of properties, and I don't really have time to go through all of them, but there is a bonus problem that you can work on this. It's called the minimum energy delay property, and this is kind of related to the example that this chapter started with. When I put an all-pass system in, I increased the group delay, and then that was making it a non-minimum phase system. And remember, as a result of that, the waveform took longer to go through that system than it did the other one. Even though one started earlier than the other, it still caught up and passed it. So a property of minimum phase systems, though, is because both the poles and zeros are inside the unit circle, they get the energy through the system faster. So we have this minimum energy delay property. And there's an example in the book that looks like this. It says, here's 4 systems, and this is the bonus problem. It's very similar to this example. And it looks at these 4 combinations. And you can see the first one is, well, what do you see? I shouldn't say that. Which one is the minimum phase? You just have to look at the top left, right? So that's the good guy. But suppose you didn't know that at first. So this example just goes and works with the impulse responses. So the minimum energy delay property says that the accumulated energy as it transfers through a filter of this impulse response will be the sum of the squared values of the impulse response, starting at 0, going to 1, adding in 1, 2, 3, and 4. So when you go through that math, and this is what that homework problem is, it computes those sum of the squares, the partial energies, and it's the system that rises up the fastest, which was the minimum phase system. It gets the energy through faster, which means it has less delay. Does that make sense? I mean, it's just a concept. It's like a physics thing. Okay, so that's a bonus problem, but it's a pretty easy one. So the last thing I have to do is linear phase systems. And there's a lot of build-up to this. But it starts off by saying all we really want to make our filtering life easy is to have a filter that introduces at most linear phase. And what this picture is showing is I'll take any magnitude response that I find useful, flat in the pass band, good stop band attenuation, and I want the response to my filter to have that magnitude response. And then I just want the phase to be this nice linear phase, because I know if I take the derivative minus the derivative of that phase, I'll have constant group delay in the band. Just tell me how to make filters like that. And that's what this section is about. So there's a lot of hemming and hawing around, kind of getting motivated about how a sinc function could be ideal linear phase. The problem is it's got tails that go from minus to plus infinity, so we can't do that. But we can truncate it, and part of the motivation right here is that we're going to be heading in the direction of this type of impulse response, but we're going to chop it off so that if you chop it off, you can slide it over and not have any tail for n less than 0. That was a concept from the very beginning, right? Causality. So that leads into this concept of generalized linear phase, and more discussion on that, a lot of grinding around in here, which comes down to, at the very end, it comes down to an equation that says, and this is just the nature of engineering math, I think, that we've all dealt with. You come down to a condition like this that says, if I want to build a filter based on a sinc function, but I want to have the condition that it's causal, I want to have the condition that it's linear phase, you end up with something that looks kind of impractical. It's not a design equation. I mean, how do you work with that? I mean, you think in your life so far you'd say brute force, I'm just going to try. But if you see something that looks kind of insurmountable, you'd say, even if I put a computer to work on this, it seems like it could be a long time figuring out by trial and error what's going to work. So the generalized linear phase idea is possible, and the fundamental property, the key property, is either even symmetric coefficients or odd symmetric. So this bullet right here pretty much summarizes everything. Even gets it, but and then odd gets it. So these two equations here saying we can show that these are generalized linear phase if you just make a filter that has coefficients that are the same at either end, moving towards the center, that match, and then equal and opposite moving from end to end. So that's the life of simplicity, and that is in essence what the linear phase FIR filter is. If you were to look in any design anywhere, you need to look for symmetry, and that's what people arrived at a long time ago, that this will do it for us. So there's a total of 4 types, and I'm going to give you the high points of that here, and then we'll be able to get on to the exam overview. The 4 types are: M is even or odd, and the filter coefficients are even or odd. So M, even or odd, is the length of the filter. The length of the filter is actually m plus 1 total coefficients. The polynomial order is m, and that's even or odd. And then the coefficients are either symmetric, both up, both down, from either end, working into the middle, or odd, up and down as you move across. So type 1 is even and even. So with a type 1, it's perfectly symmetric, and the filter order is even, which means that there's a center coefficient that is stands alone, because the length of the filter is m plus 1. So if you have m, then you've got m over 2 coefficients, the front end and the back end, and then you have a single coefficient standing up in the middle. If you go into type 2, it's just an even number of coefficients front and back and no center term. And the math that I have in here is just showing you that it comes down to that generalized linear phase form. When you say take a type 1 and go through the look at the frequency response, plug in the symmetry factor, you end up with something like this, and this is what generalized linear phase boils down to for all these 4 types. You have some phase term out in front, and then in the middle of that you've got something that's purely real, because you only see cosine in there and the coefficients are going to be real. So that means the magnitude of that could at most change sign, but that could be grouped into the phase response if you wanted to. So that's the conditions to make generalized linear phase, something that's a pure magnitude of a desired response, and then an e to the j something term. Type 2 works out the same way, just a little bit simpler to write it out, but it still has the same idea. Type 3s and 4s are the odd symmetry, so we have the minus sign in here, and it's either m is even or odd. And I know I'm going fast, but all the math details are the details. I think as a user, I look at certain properties, and this is what I look at if I'm given a set of coefficients. If somebody says, I say, we want to model our system, maybe it's from FPGA, maybe it's code running on an ARM core or something. Where are your coefficients at? They're in a header file if it's in an ARM core, and it's going to be in a coef file that Xilinx likes to use for coefficients because they've got synthesis tools. But I look at those coefficients, and if they're hex, I'll get them into fixed point integers. I mean, whatever. Still, I'm looking for symmetry. So in the real-time DSP lab from this semester, I have tools in Python that will take the designs in Python, convert them to fixed or floating point FIR filter coefficient header files, and write those header files. And then in the microcontroller, you use those header files. And those header files were useful to me when I worked on a project at the previous company when I wanted to put it into an ARM core and delivered all this stuff to the guy that put it in the microcontroller or in the embedded system. But anyway, here's the summary of what the 4 types are. And this is kind of easy to remember. If m is even, m plus 1 is odd, so it means you've got a point of symmetry. This coefficient is unique. The other coefficients are all pairwise connected to each other in even symmetry. Type 2, m is odd, so when you subtract 1 from m, you get an even number, so that means the point of symmetry is at a half integer, no coefficient there, but again, you still have the symmetrical coefficients. Easy, right? I mean, it's a rule, but it works. The odd type, type 3, is even m, so you do have a coefficient all by itself, but that has to be 0 if it's going to be an odd order filter. I mean, it's going to be an odd symmetry filter. So these are equal and opposites here, but in order to abide by the definition of odd symmetry, you can't have that isolated term be anything but 0. When you go to the type 4, you don't have a central term, but you have the nearest neighbors there, and those are just equal and opposite. When I first saw this, I thought, wow, this is so confusing. Why do we have 4 types? Well, the filter synthesis tools will synthesize into one of these 4 types for us automatically. If you say, in digital comm, I prefer a type 1 usually. Why do I prefer a type 1? Because I want to have a delay that's an integer delay, and that's what I would get here. Whereas here I would not. If you're an FPGA person, you might say, no, I don't want that. I want to have an even number of coefficients, and I want it to be a power of 2, let's say. So then they might favor a type 2, but it might depend upon, what the delay properties of the filter are. It's still going to be a constant group delay filter, but from delay standpoint, I like the type 1 better. So I might bump the order up or down. In my filter design functions that I wrote, I have a function, an optional argument called bump, which can bump it up. After it does the design, you can say bump it up 1 more, just so that I get it to go from a type 2 to a type 1, or vice versa. You can kind of tweak it a little bit. You can over-design the filter slightly. So the next big thing is, how do the filter coefficients lie for these linear phase FIR filters? And you can go through the analysis here to just see what are the conditions. But again, pictures kind of rules in this case. For linear phase FIR filters, zeros have to occur in certain types of clusters, and the fundamental cluster is if they're not going to be on the unit circle and they're not going to be on the real axes, then in order to have real coefficients, that's a bunch of ifs, right? If. But if that's true, then zeros always occur in quadruplets. My wife had twins, so I can relate to multiple birth pregnancies. I would have not wanted to have quadruplets in my household, but some people have them, right? So I always think about birthing, and whenever I think of linear phase systems, I think, yeah, they're 4 at a time. You can't slap down just one if you want to have it not on the real axis or on the unit circle. If you want the zeros to be on the unit circle, then they can occur as a pair because the conjugate just balances it to make real coefficients. And then the third condition is if they're going to be on the real axis, they're just going to be in a pair. So the general case is quadruplets, and then twins or pairs, 2 at a time. And then finally, you can have 1 at a time if they're on the unit circle at either -1 or +1. Type 3 and type 4 are similar, but there's some additional rules that go with them. So I have this picture that kind of summarizes what's going on there. And this has been known to show up on the final exam where I give you part of a pole zero plot. I'll just describe how a homework problem might, or an exam problem might work. I give you a plot for a filter, and I'll give you some of the zeros down on the filter, and I'll say that it's a linear phase FIR filter. Fill in the missing zeros. And these are the rules. And by the way, remember the final is open book, open notes, so these things will be available to you. So for the type 1, that's there's an example of how that would be. We can see there's 2 quadruplets there, and those guys are twins, and then that's a conjugate pair. The poles that you see are just all stacked up at 0. They're just balancing out the zeros. That's all they're doing. They're just along for the ride. And when you go to a type 2, the necessity is that it has to have a 0 at z is equal to -1. And if you don't like that in your design because you don't want to have a tack down point there, then you have to go to a type 1. Types 3 and 4 just have more constraints. A type 3 has to have a 0 at 1, a -1 and 1, and a type 4 has to have a 0 at 1. So neither of these are generally low-pass filters. They could be bandpass filters. There actually could also be Hilbert transforming filters, which is something you learn about in Comm Systems 1, and I have that in real-time examples. I'm actually maybe going to do something with that in your project. I don't know. Have you ever heard of a Hilbert transforming filter? You had it in comms, right? But in DSP, they are used, so kind of intriguing. So then I have a bunch of examples in here. Nothing too thrilling. You can just see, though, that the group delay is always 0. I'm going to prefer to just jump over to my notes over here. Where I had that in here. I could run this in real time too. I've got it right here, but here's where I did a filter design where I just did a equal ripple high pass filter, and I said end bump equal to 2. And here's what the pole 0 plot looks like. So If you've never seen one of these before, let's just kind of study it. It's pretty obvious what's going on once you get tuned into it. What do you see in here that makes it linear phase? Or is it linear phase? I mean, that could be a question. Is it linear phase? You're talking about over here? These are all quadruplets, right? There and there. Everything's a quadruplet. That's a twin or a double. And then on this side, there's 1 0 that's on the real axis and has to occur with its conjugate reciprocal, or just reciprocal. And then these are all pairs. So it meets that requirement. And the fact that there's 52, or you could count all these zeros and you should get 52 also, that's the order of the polynomial, so the length of the coefficients in the filter should be what? M plus 1, which would be 53. So the order of the filter would be 52. The number of coefficients that you'd have to store would be 53 for this filter. Now, do you know it's a high-pass filter or not? Just guessing at it from the pole zero geometry we went through. What do you think? These are all on the unit circle, so those would all be tack down points, right? In terms of what we were looking at from geometry. If you swept around on the unit circle for your frequency response, you'd be getting hammered down to 0 over and over again. These quadruplets here are defining your passband, is what it turns out. And I have the picture of that, I'm pretty sure I put in here. Yeah, there it is, right there. I like, myself, the idea of having both views. The pole zero plot lets you understand what's behind it. As a implementer and somebody that wants to get a desired outcome for my system, they won't be as necessarily concerned with the zeros and zero locations, but they'd be interested in that. Did we design it? We designed it to get 80 dB of stop band attenuation, and then we set so much ripple in the pass band, and then the transition band was part of the design requirements too, and that's what drove the order of the filter to be so large. I think I'm ready to move over, just double check where I'm at here. Just a bunch of different examples I had in here similar to what I just went through. Just verifying everything holds up. Frequency sampling, FIR, is talked about in here, but it's just interesting to understand how it works. These days, the art of filter design under the hood is not as much an issue as it is just using tools. Just like in microwave circuit design, it morphed a lot to just using tools to design filters, whether it be a microwave distributed element filter or a digital filter. Just get the coefficients or get the transmission line elements and so on. So,
when you design a filter, do you generally start with the pole zero plot, or do you start with the map?
I start with the requirements. So if I was designing a filter, I would do it right from here. Let's see, let's go over to this. I would go right from here, and I don't think this will design. Yeah, it will. Nope, I didn't design it. I didn't call that in yet. So I called that in way up here. Get those two imported. By the way, if I was doing this as a matter of practice, I would move this cell right up here where I imported those design functions. I would put them right at the top because it's too confusing to look for stuff in the middle to me, but I did that because I didn't have them at the very beginning. So now this should run. And I did a remez, and I also did a design that was a Kaiser window-based design, and I would maybe trade those off. So if I was doing that, I might call this version A, and then I might do something like this. Interesting, right? Equal ripple, because we allow ripple in both pass and stop band, is more efficient. In this case, the requirements of both filters were the same. The Kaiser window took 87 taps, and, and the other one took 53. Is that intriguing, or just like, wow? That would be less real estate in FPGA or something. And then I could go down here, see how I could put in this thing. I can just put that in down here. I can overlay them on top of each other. Except I'm down here. Let's see. Okay. Yeah, I need to put this back to dB. You can see the group delay is constant, and it's just half the length of the filter integerized, so it's just constant. It's half of 87 and half of 53 are those two values. But if I wanted to see the shape of the filter, I have to go into here, and if I want to remember what that is, I have to go back up. I have to go back up to this function and do Shift Tab, and I will see what the various options are for this function. dB, where I was in group delay, in samples or in seconds, I provided both of those, but let's put dB in here. And I could tweak that to see it better. I could go Y-lim, so now you can see why the Kaiser window takes more taps. With the equal ripple, we're just saying, just give us an equal ripple level, more efficient. Here, we're meeting that requirement, right in this neighborhood, but then it continues to go down. So we're getting maybe more bang for our buck. Well, we're getting more bang than what we need. It's a trade-off, though, and that's I wouldn't say one's right or wrong. It's just the way it works out. I'm ready to talk about the exam, though. I don't have to go through every problem, but I do have it right here. So before I move on, though, what I didn't talk about is all pass and minimum phase can be also worked in with linear phase. So in this first simple example here, let's just finish that off so you can have that as needed. I probably will go all pass rather than linear phase. I'll save the linear phase for the final. But if we wanted to do this example here, where we had the pole and the zero, what we have to do instead of thinking all pass for our synthesis, we're instead going to think of linear phase. So what linear phase would have to do to get the zero inside to make it minimum phase is I put a zero inside of here, right with the linear phase, and then I will have the opposite zero there, the conjugate reciprocal, just like we did in the all-pass form. But then because the minimum phase, or the linear phase, is going to bring with it two poles rather than one, which is part of the all-pass, it'll modify the minimum phase result to then have another pole out here and another zero in here, because it's making up for what this thing is doing. It's just a variation on the same idea. You would get the minimum phase, but then it would be paired up with a linear phase. And there's some more examples in here. Okay. I guess I didn't open this up yet. So I have it due at 5 p.m. on Wednesday. If you'd like to have a Slack meeting, I realize next week is called a break week, and I'm probably could be called onto the carpet for this, but I'm doing it because this is a new event for me in my entire life of being here. We always had class during part of next week, and I'm just not wanting to give it up, so you can learn more. The idea of Wednesday is that if you're going to be with family all day Thursday, which I will be part of our Thanksgiving dinner since it's at my house. I definitely understand that, but if you wanted to have a meeting Monday, Tuesday, Wednesday on Slack, you can just ask for it at any time. If you want to have a discussion with me, we can do a huddle on Slack. This problem is pretty straightforward, multi-rate. This one, number 2, is exactly the equalizer that I was talking about. We're going to put in a bit stream, and the channel is going to be an FIR distorting channel, and the ideal signal after it goes through a match filter, which is defined in the problem, should come out with an I pattern that looks like this. Have any of you seen I patterns? Okay, so you know what they're about. I give you a link down in here to something from COM2, and that's on the website, so that link will take you there. So I'm defining what the distorting system looks like, and here's the badness right there. See what that is? That's got a 0 outside the unit circle. So you want to equalize it, but you can't, because if you tried to build the inverse of that, you'd have a pole outside the unit circle. So you have to go into this minimum phase idea to do that, and you can just pattern this after that example. The only difference is you're going to evaluate it by throwing on this match filter, and then you'll be seeing what the I pattern looks like. You'll see it both without the equalizer and with the equalizer. So this looks beautiful. The distortion, slap that on there, it'll get pretty trashed up looking. Put the equalizer in, it will get fixed considerably, but it will not look quite perfect because there's still some phase distortion in there. And you use a function that's in the SIGSYS library called NRZ bits, non-return to 0 data bits, and it also returns the matched filter inherent. We're using a rectangular pulse shape. It could be root raised cosine, but B comes out of that, and that is your matched filter that gets used later on. When you're going to plot an I plot, you will take your output signal and then pass it through the matched filter right there. And this is kind of the setup for it right in here. It's kind of fun. Pretty simple problem, really, but you got to understand some things and take it through its paces. I don't know. I'm probably crazy, but I want you to have some exposure and you'll feel a little bit comfortable about stuff. I want you to say when you see something later in your life, I did something on that, just a little bit. Maybe I didn't learn enough, but I have a starting point, and then you might convince a manager to let you try something out and let you start doing some analysis. Okay. This problem is sort of what you had on the last homework, except now I've thrown in a filter. So I've got an analog filter, and I'm going to model this system as if it's an anti-aliasing filter, and I'm going to simulate it using a Butterworth low pass in the DSP domain. So that's on the next page, but the model for the filter as a Butterworth is it's a 7th order Butterworth low pass filter. We're working at a clock rate of 200 megahertz, and we're going to have signals at 50 megahertz and 90 megahertz, and you're going to be studying the signal to quantization noise ratio coming out of this. So you're going to want to do an analysis of this based on the roll-off of the filter, and then see what the signal to quantization noise ratio is using the ideal analog filter is what you're going to do. But then you're going to build a behavior level simulation model according to this using Python. So you'll oversample at 800 megahertz and just build this Butterworth filter. It'll be A and B coefficients will come out of it, and you'll use that in your model to simulate what's going on with the in the analog domain. Then you'll decimate by 4 to take it back to 200, and then come in and quantize it and see what's going on with the signal to quantization noise ratio. And because this is a tricky little calculation to get the SNR calculated correctly, I've got this formula I'm giving you to say, how do I get there? And you're going to get there by taking a measurement on the spectrum, the power spectrum output, the power spectrum estimate at the output, and then apply this equation to it. So I have a function that's in the package called Simple Spectrum Analyzer 2, and in it, it's going to use another function that's in this module, SA new. So I've got two pieces to that, and that is over here in the Python notebook. And there's a zip package that has a notebook for calculations, and then it has a module of Python code that you use. And because spurs can show up when you simulate something like this, I didn't use exactly 50 and exactly 90. I picked values that were a little bit away from that, so I would get rid of the spurious responses, and I get a really nice spike, and then I get a constant noise floor. So you're going to have to measure the power of the signal at that point, and then you're also going to have to measure the noise floor around it. And so how do I do that? I do that in the notebook. Let's see. So here is the function that you'll have, and you can run this and use it, of course, to do your spectrum estimate and then plot the spectrum. And you'll see the noise floor from the quantization noise in the simulation, and then you'll also see the spike. In order to get the noise power measured, I'm giving you this function, and what this function will do is you'll have a spike right here, and then you can set two bands with this function that you want to measure noise power adjacent to the spike. So I set one above, or one below and one above, and then I get those estimates out of this function, which will be this mean value over that interval, and then I add them together and divide by 2. So I just get a measure of the noise floor, and that goes into the formulas. There may be some questions on it, but it's pretty straightforward beyond that. And you get results that are extremely accurate within a dB of the theoretical prediction using the quantization noise model, which seems really crude, but it comes out really accurate. This is just being very meticulous and careful, which is consistent with things I want you to learn about. So back over here to the exam. The other problem that's a little bit, but really that involved at all, is you're going to use, this is a random process problem, so you're going to consider white noise of this variance. Variance 5 is going to be going through this Ramez bandpass filter, and you want to see what the noise variance is coming out of the filter. So you've got a simulation means will be to just simulate it and then drive the noise through to that variance and then measure it using the VAR function in Python. And then you're going to theoretically calculate it using something that was actually developed in problem 2.92b, but have no fear. I've got a comment section in here to give some hints, so I'm telling you this is how you're going to do it. You're just going to get the impulse response of that filter, and then perform this calculation, and this will analytically come up with the noise power at the output, and then you'll measure it in your simulation and see that, again, it's very, very close. I have a proof of how that works out, but that doesn't really matter. I realize you already did that problem. I haven't graded it, but I'm going to be getting that grading done and get papers back to you. But these are the three sort of Python-based problems. The other ones are pretty stock kinds of things to do. But the eye pattern is intriguing, it's interesting, and it works really, really well. The spectrum analyzer problem is intriguing. You get to do analysis that's simple. It works really, really well. And then this works really well too. This problem, in the past when I've used it, people have gone off and made it hard. It's not hard. This is an easy calculation to do. Once you design the filter, you get, what do you get when you design a filter? You get A and B coefficients. If you want to get the impulse response, you drive it with what? A delta function. And you'll get the impulse response in this long vector, and then you'll have those numbers. So you have to take that extra step, but that's not a hard thing to do. And then the simulation just takes care of itself. I give hints on that in here too. I wish we could meet again, but right now we're going to take off and be on our own. Hopefully the others will get on board here. I'm going to stop the video though.